All right, so I'm recording again. Welcome, everybody. Thanks for being here. Can everybody see okay and hear okay? And yes, Nathan, I am recording. So my original plan was to record these lectures ahead of time and then post them, kind of put them in the homework assignment. And so I actually made lectures yesterday, but they didn't have audio. So I'm recording this lecture, and then what I'm gonna do is I'm gonna put this into, I'm gonna share this publicly. It's just gonna be on, I'm just gonna put this on YouTube or whatever. And I'm gonna have it accessible so that you can just, put it in the homework file essentially. It's gonna be in the homework file, and you can just all be there in one screen. That said, if anybody has any questions, you can just unmute yourself and say, oh, hey. Otherwise, you can text me, you can do this group chat thing, which people have already done that, but I may miss it, right? I might not see it because I don't know if I don't think it dings to me. The board is a bit out of focus. You might need to write a little big so we can see it. Yeah, I know, I understand, it's a problem. I try to, it kind of goes in and out of focus. A lot of this depends on the lighting, which is a little bit variable, and it's hard to get it right. So I'll do what I can. Holler at me if you can't read it, okay? So we're gonna go from there. I'm gonna write big, try to go slowly, and we'll work from there. So today, what we're really going to be talking about is stability of linear systems. Linear systems. Right? And so to give a little bit of context to what we talk about when we talk about stability, let me just kind of give an example, all right? So this is an example that is going to be in your homework file, but this is a state space representation of the simple harmonic oscillator. And so this thing, if you take in the first controls class, we talk about this system all the time. It's just a generalization of the Newton's laws we deal with. Just the, somewhat more general case of the Newton's laws that we see all the time, where what we have here is, this is the natural frequency, this is the damping constant. So this is damping. This thing, omega naught, not omega naught squared, is the natural frequency. And you're going to do all these calculations in more detail in your homework, so I'm not going to go into detail on them. And so the beauty of having these lectures recorded is you can always just go back to the piece of the video and match it up with what's going on in the homework assignment. So roughly speaking, what's going to happen is there's going to be a case where omega naught is positive, zeta is positive, and zeta is small. And what's happening here is if we draw out the trajectory of this is what's called a phase plane. So if we looked at x1, x2, and we saw what happens to this thing over time, so if we just started here, what's going to happen is this thing is going to spiral into the origin over here. So this is just taking this, what we're plotting is how the trajectory of x1, x2, right? So this is a two-dimensional vector. And we're plotting how this thing evolves as time goes on. And what happens is in this scenario, when your natural frequency is positive and your damping isn't too big, it's just going to do this spiraling thing. If your damping is higher, it's not going to spiral. It's just going to go like that, go straight to the, nearly straight to the origin. So it won't have this spiraling behavior. And what we see when we have this behavior of spiraling to the origin, this occurs when the real parts of the lambda, or if this is an eigenvalue of A, when the real parts are less than 0, right? When the real parts are less than 0, this thing has this property that it spirals into the origin. And another variation that we'll see on this is when the real parts are purely imaginary. So in your homework, I'm going to ask you to find values of zeta and omega 0. And those of you who have taken the first controls class, you're probably going to know exactly how to do this. I'm going to ask you to find values of zeta and omega 0 such that you have purely imaginary eigenvalues. So when you have purely imaginary eigenvalues, when the real parts of the eigenvalues are 0, the phase plane looks something like this. You're going to start, if you started here, x1, x2, if you started here and you examine and you plotted what the trajectory does over time, it's just going to go around in a circle. And it's going to come back exactly to where it started. It's just going to keep rattling around and around and around here. So if you just watch that thing go over and over and over again, if you just plotted it, if you started off here, you're just going to run around in a circle. And if you started it down here, you would just go in a circle. If you started off anywhere, you're just going to go in a circle. Wherever you started, you're just going to stay on that circle. Okay? That's what, and we'll see that in the homework. And then the other case that we might have here is when omega naught is positive and zeta is less than 0, this is negative damping. So negative damping would be like, rather than trying to slow you down, it's trying to speed you up. As you might expect, instead of slowing your oscillator down, you're speeding your oscillator up. If you start here, you're going to spiral, but instead of spiraling in, you're going to spiral out. All right. We're going to spiral outward, and this is going to blow up, and it's actually going to be sort of getting larger, gets larger exponentially quickly. Right? So this is going to get big, and it's going to get big very fast. Now, the final case that we're going to want to deal with here, so these are the sort of behaviors. Let me just kind of write a checklist of behaviors that we're seeing. Goes to origin, and it's actually going to go to the origin exponentially quickly. The second behavior that we saw is it simply oscillates around the origin. But it oscillates with bounded magnitude. And diverges to infinity. Now, there's going to be sort of two cases of diverging to infinity that are going to arise. We're not going to really worry so much about the distinction because whatever, this diverging to infinity is just something we typically don't want. So in this case, we're diverging to infinity exponentially quickly. And we're going to have one more case where we diverge to infinity. And it's this one. So if we looked at this thing, so let me just kind of see what's going on here. This is when the real parts of lambda were less than 0. This is when the real part of lambda is equal to 0, but there's going to be a bit of a caveat here, because what we're going to see here is this is when the real part of lambda is greater than 0. There's going to be actually two scenarios where this two scenarios where this is actually diverging to infinity. Because what's going to end up happening is if we plotted this thing out, okay, if we started up here, and in your homework you'll have to solve this more explicitly, but if we started up here, this is x1 and x2, and we plotted out what the trajectory is going to do, if we started here, this is our state is going to go like this. If we started down here, it's going to go like that. If we started down here, it's going to go like this. Started down here, it's going to go like that. In either scenario, in either case, this is diverging to infinity, but what are the real parts of the eigenvalues? It turns out that the eigenvalues of this thing, there are two eigenvalues. It's just both at 0, so it's algebraic multiplicity 2. In this case, real part of lambda is equal to 0, since only eigenvalue is 0. So what's going on here is there's a little bit of a distinction, and it's a subtle distinction between what's called algebraic multiplicity and geometric multiplicity. We're going to get into this a lot more in detail later on in the class today. That's a good amount of what we're going to talk about today is this distinction between algebraic and geometric multiplicity, just so that we understand what's going on with this particular problem here. So what's going on, when we had that scenario, we said this was actually, and we'll talk about this more later, this is when the algebraic multiplicity equals to the geometric multiplicity. And we'll talk about that more. Or real part of lambda is equal to 0, and the algebraic multiplicity is greater than the geometric multiplicity. All right, so this is just a high-level overview right now. Now let's go and look and see what is going on over here with this thing right here. In this case, the characteristic polynomial of this thing is lambda 0 minus 1 lambda. The characteristic polynomial of this matrix is equal to this, which is just equal to lambda squared. And so this is 0 is an I of algebraic multiplicity 2, because this is a repeated root of degree 2. That's what the algebraic multiplicity means. It's how many times the root is repeated when we look at this characteristic polynomial. But the geometric multiplicity is 1. So all of you, if you don't know what a kernel is, I've been talking about kernels many, many times. So if you don't know what a kernel is, please look it up. It's the null space of a matrix. It's the space of things that if you hit the matrix, it's zero. Because I'm going to need that when defining this thing. The geometric multiplicity of an eigenvalue lambda is the dimension of the kernel of lambda I minus a. Okay, so it's the dimension of that null space. And so in this case, of course, I can flip the sign of this thing just to make the math look a little cleaner. A minus lambda I. So let's see why the geometric multiplicity of this eigenvalue 0 differs from its algebraic multiplicity. So we have AB in the kernel of A minus lambda I. So any vector over here can always just be represented with two numbers. So I'm just going to represent any vector here if and only if A minus lambda I AB is equal to 0. That's what the kernel is, right? It's just the set of vectors that if I hit this matrix, I would go to 0. That's the kernel of the matrix. So let's see what this is. In our case, lambda is just 0. So we plug this thing in. It's 0, 1, 0, 0 times a b. So we get b 0. And so in order for this thing to be 0, this tells us that b is equal to 0, a is free. And so in particular, what we see is in this scenario, we must have this thing look something like this. Anything like that is in the kernel of the null space. So this thing is actually equal to the image of this vector, because that is a basis for all things that look like that. So what we see over here is that the dimension of this thing, the dimension of this space has got to be 1 because it's got a basis of size 1. So in this case, 0 has geometric multiplicity one. All right. So that is sort of the distinction that we're going to need to deal with when thinking about the overall behavior of linear systems. Namely, we're going to have to deal with what are the, namely, we're going to have to deal with a little bit of a distinction between algebraic multiplicity and geometric multiplicity. It's in the end, it's going to, all of these things are going to be thrown under the ruggable, but in presenting the main sort of theorem, we are going to need to deal with this. So let's go deal with this a little bit more generally. So what we want to understand is to understand if x dot of t is equal to a x of t, we want to know when does x of t remain bounded? When does x of t converge to the origin? And when does x of t, this is the norm of x, go to infinity, where the norm is defined like this. Here, this norm, this is what's called the Euclidean norm. This is defined by x of t transpose. X of t. So that is the norm. That's just what we call a norm. And this norm is really, it's the Euclidean norm because in 2 dimensions, if we had a vector like this, x1, x2, just by, what is that, the Pythagorean theorem, this distance from here to here is actually square root of x1 squared plus x2 squared, which is exactly equal to the norm. Okay, so this captures our natural notion of size of a vector in terms of what we would think about in terms of standard geometry as the distance between points. Okay. So, in particular, the distance between the vector location and the origin is exactly captured by this norm. So we want to know is, when does the vector go to infinity in terms of when does its size go to infinity? Those are what we're going to want to deal with. Right? And so these are really sort of long-term behavior questions about the state that we want to answer. We want to answer when does the state stay bounded, when does it converge, and when does it diverge? We want to answer all of these things. So the quick preview is if real part of lambda is less than 0 for all i's, and this is, it stays bounded, so it remains bounded if the real parts of all the eigenvalues are strictly negative, if the real parts of lambda are all less than or equal to 0 for all i's, and if real part of lambda is equal to 0, the algebraic mult equals geometric mult. The algebraic multiplicity equals the geometric multiplicity. That's what we're going to require. That's the bounded case, and this is any other condition. So the other conditions are, if any of them have strictly positive real parts, it's going to pull up. If you have an eigenvalue with real part 0 with algebraic multiplicity greater than the geometric multiplicity, because the geometric multiplicity is always less than or equal to the algebraic multiplicity. So if you have algebraic multiplicity greater than the geometric multiplicity, then it's going to also blow up. So those are the 2 scenarios. So this is what we're going to call stable. This is what we're going to call asymptotically stable. And this is what we're going to call unstable. Oftentimes, this is just called marginally stable. In the case where, oh, no, this is the asymptotically stable case. Sorry, because I was just pointing arrows in the wrong direction. This is the asymptotically stable case. And if it remains bounded, but it's not asymptotically stable, bounded but not asymptotically stable. So if it's bounded but not asymptotically stable, called marginally stable. And otherwise, it's called unstable. And let me check if my other pen is any better than this. It's slightly better. I'll use that for now. I'm going to need to get new pens. This whole thing has caused me to need pens a little quicker than we thought. So what I'm going to spend most of the time today working through is showing exactly why this is the case. Okay, that if all of our eigenvalues have strictly negative real parts, then everything goes to 0. If we have this other condition where we might have something right on the imaginary axis, so its real part is 0, it'll stay bounded as long as this multiplicity condition holds, and any other condition it goes off to infinity. So that's what we're going to be working to show. Now, what we're going to need to use in order to show this is what's called the Jordan canonical form. All right, so when we talked before, we were oftentimes assuming that matrices could be diagonalized. So when we originally talked about this e to the AP, most of the matrices we saw could be diagonalized. And to be honest, most matrices that you'll see in practice really can be diagonalized, but in general, that's not true. So in particular, the Jordan canonical form looks something like this. A is equal to, if we had V, I'm going to have to put the V inverse over here, V, J, the inverse, where this thing is J, this Jordan matrix, so this Jordan matrix is named after the basketball player Michael Jordan. He, was doing linear algebra in his spare time. This thing looks like this, where J is equal to J1, J2, Jm. So these are this is block diagonal. And the specific form, so these what are called Jordan blocks, have the form there's only a few types of ways that these can look. Or lambda 1, 0, 0, lambda 1, 0, 0, lambda 1, 0, 0, 0. So what we're seeing here, the pattern that we have here is that it's always the form of a matrix with lambda on the diagonal, ones above the diagonal, and zeros everywhere else, where lambda is eigenvalue. So, for example, the kinds of things you might see in a homework assignment that I'll give you, we might have a matrix that looks something like this. The Jordan block might look something like -1, 1, 0, -1, 0, 0, 0, 0. I'm just drawing these to highlight the distinction here, where this is going to be our J1 and this is going to be our J2. This is our J1 and this is our J2. Now, it turns out for every matrix, the Jordan blocks are uniquely determined, okay? So every matrix has a unique collection of Jordan blocks. Now, the ordering of how they show up along this block diagonal can change depending on how you order the columns in this V matrix. But the form itself is the same. These J1s are completely, this J1, J2, so on, are completely specified by the matrix itself. So this is unique. This tells us what we need to know about the matrix. And it tells us what we need to know about the eigenvalues, geometric multiplicity, and algebraic multiplicity. So from this Jordan matrix, we can actually read off that the eigenvalue of -1 here has, so we can see here, because this is an upper triangular matrix, this is going to have eigenvalues of -1, -1, and 2. Okay? And -1, because it shows up twice, is going to have algebraic multiplicity 2, and 2, because it shows up once, is going to have algebraic multiplicity of 1. And because we have this non-trivial Jordan block here, that's going to tell us the number of Jordan blocks corresponding to a particular eigenvalue are going to tell us its algebraic multiplicity. So in particular, this -1 has algebraic multiplicity 1. So from the Jordan form, we see has algebraic multiplicity 2, alg mult 2, and geometric multiplicity 1. Because there's one Jordan block here, and very similar to the analysis that we did on the very similar to the analysis we did with that simple matrix, because that was just a special form of a Jordan block. We see that the dimension of the kernel corresponding to this eigenvalue is going to have dimension 1, whereas it's going to show up twice. So you can just look at the geometric multiplicity and algebraic multiplicity from the Jordan block. One quick thing that I would just like to mention is that the characteristic polynomial of A and the characteristic polynomial of J are exactly the same. And if you haven't seen it, this is a nice little collection of properties of the determinant. So I will just very briefly show you it. So if A and B are square, then det AB is actually equal to det A det B. This is called the homomorphism property of the determinant. So you can always take the determinant and split it up by the products. So that has a lot of nice, interesting consequences. For example, that identity, which we know the identity is just has determinant 1 because the determinant is always the product of the eigenvalues, and all of the eigenvalues of the identity matrix are 1. So this thing is equal to 1 is equal to det V inverse. If this is an invertible matrix, we know that it's det V the inverse. And so an interesting little fact that we have that we're going to use quickly over here is that this is equal to 1 over det v. That's kind of neat. So what we can see from this basic property is that A and J have the exact same characteristic polynomial. So in particular, all the eigenvalues are exactly the same, and the multiplicities that we can read off from this matrix can be read off. You can read off from that matrix, carry over to the original matrix A. So det ni minus A, which is equal to det lambda I minus V. This is just how we were defining the Jordan form as there is some matrix V that makes this thing true. And of course, I can always represent I as V inverse. So this is equal to det of, by just skipping a step slightly here, but we've done this sort of analysis several times in the past. J the inverse. So what we see here, so all I do, if you put these, if you multiply this through, you're going to get this guy. Multiply this through over here, you're just going to get the identity because the V and the V inverse cancel out. And so we get det V det by this property lambda I minus J det the inverse. And now these are scalars, right? Because determinant's always a scalar. So this guy and this guy cancel out to give you 1. So we get left with det lambda I minus J. So they have the exact same characteristic polynomial. In particular, we can read it off from the diagonal of that matrix. All right, cool. So, going back to the story before. I see a hand here. What does that mean?
Someone has a question, I think.
Oh, far out, man. That's great. Ask it.
Can you give an example of a case where an eigenvalue has a geometric multiplicity that isn't 1?
A geometric multiplicity that isn't 1. Yeah, sure. So, perfect. The identity is exactly a case where this has two eigenvalues. This has a repeated eigenvalue at 1, right? And I minus 1 times I is equal to 0, 0, 0, 0. So the kernel is the whole space. So if you have repeated eigenvalues, so basically, if your Jordan blocks didn't have these little ones here, right? So another simple example would be like if J is equal to 2, 2, 1. A slightly less trivial example looks like this, okay? Then J minus 2I is equal to 0, 0, 1, or 0, 0, minus 1. Let me just write this more systematically rather than really quickly. And so then what's going to end up happening here is that the kernel of J minus 2I is equal to the image of 1, 0, 0, 0, 1, 0, like that. So this has dimension 2. So the geometric multiplicity, the geometric mult equals to the algebraic mult, both equal to 2 in that scenario. So yeah, so it's basically anytime you have repeated Jordan blocks, so because you can think about this, this is just a simple Jordan block. These are each Jordan blocks. The number of Jordan blocks corresponding to an eigenvalue is its geometric multiplicity. but the number of times that eigenvalue shows up on the diagonal is its algebraic multiplicity. So in particular, if you ever have a non-trivial Jordan block, one of those ones where a 1 shows up off the diagonal, then you know that that eigenvalue has smaller geometric multiplicity than its algebraic multiplicity.
What does that say?
Yeah.
If A and B are what?
If they're square, just so the determinants exist. If they're square, then the det AB is equal to det A times det B. Make sense? I mean, it's not obvious at all, but it's true. Okay. Right. So the key thing here is we can reduce the questions about the behavior of the system to questions about this Jordan matrix here. And the reason is recall that x of t, if x of t is equal to a x of t, then x of t is just given by our matrix exponential. And if this thing has a Jordan decomposition that looks like this, v j v inverse x of t, by that derivation that we had before, and just so you know, please do just speak up if you have a question, because it's always hard for me to tell. It's hard for me to tell if somebody doesn't see something because the screen is small in comparison. So we derived this several times in the past, that if you had the VV inverse, you can just pull these off to the side. E to the J T V inverse x of 0. So in order to understand the behavior of this, it suffices to understand the behavior of this guy. Now, let's think about what happens if we had, say, 3 Jordan blocks. Say J is equal to J1, J2, J3 with zeros elsewhere. What we're going to have here is that by that same argument, we did this argument in the past that if the matrix was diagonal, the matrix exponential just takes the exponential of the things on the diagonal. Same thing holds when it's block diagonal. Using the same exact argument that we had before, that e to the jt is actually equal to e to the j1 of t 0, 0, 0, e to the j2 of t 0, 0, e to the j3 of t. And the reason, I'll just sketch it out, is because this thing is equal to k equals 0 to infinity t to the k over k factorial j to the k, but then it's equal to 0 to infinity t to the k factorial. Just like with a diagonal matrix, the product of diagonal matrices is just the product of their diagonal. Same thing holds for block diagonal matrices. So it's j1 to the k, 0, 0, j2 to the k, 0, 0, 0, j3 to the k, and so on. So then if you just take this sum into here, you're going to get each one of these terms. So that's why that's true. So what we've done here is taken the analysis of this function and reduced it to studying the properties of each of these guys. Right? So as long as we can understand the behavior of a Jordan block, we can understand the behavior of the whole system. So let's go and try to understand the behavior of a Jordan block. In particular, I just want to know, what do these matrix exponentials look like? So if ji equals to lambda, this implies e to the jit is equal to e to the lambda t. So it's just a scalar. All right, cool. That's not super interesting. Let's go and do a more sophisticated example. Let's do the next one. And I know we've worked this out before, but we're going to do it again. This is an exercise that's good for the soul. All right. If it's looking like this, what I'm going to do is I'm going to break this up into two pieces. I can write this as lambda I plus n, where n is equal to 0, 1, 0. So we have two properties that are showing up over here. N squared is equal to 0, and lambda I n is equal to n lambda I. All right. So all I did was I just split this thing up into two matrices that commute with each other. One of the properties that we learned way back in the beginning of class is that if you have two matrices that commute, you can use that exponential product formula. In general, you can't use it. But since these two matrices commute, e to the j I of t is equal to e to the lambda I plus nt, lambda I t plus nt. Because these two matrices commute, this thing implies that this is actually equal to the lambda I of t times e to the n of t. Now this thing, this is just the matrix exponential of a diagonal matrix. And as we saw, the matrix exponential of a diagonal matrix is just the exponential of everything on the diagonal. In particular, this is just a diagonal matrix. This thing is equal to, if we just plug this thing in, e to the lambda t times I. That's what this piece is. And this piece, because n squared is equal to 0, we can just do the power series expansion. The power series expansion of this thing is just Tn. It's equal to that thing. This I can be absorbed into here. You get e to the lambda t I plus Tn. All right, cool. So that is the case where we have a 2D Jordan block. Let's see what a 3D Jordan block looks like. If ji is equal to lambda 1, 0, 0, lambda 1, 0, 0, lambda, then we know that this thing is actually equal to lambda I plus n, where what we have over here is n is this thing. So in particular, n squared is equal to 0, 0, 1, 0, 0, 0, 0, 0, 0. This is just squaring that n. N is just this piece with 0, with the ones above the diagonal and zeros everywhere else. And it turns out that n cubed is equal to 0. Additionally, we have, so n cubed is equal to 0 in this scenario. And still, because any multiple of the identity always commutes with any matrix, as long as it's square, lambda I, the same argument holds, but now we just have to do one extra term. So in particular, so this argument from here up to here all holds. We just have to modify the power series expansion of this thing. So in particular, e to the ji of t is equal to lambda e to the lambda t, where this just has one more term in the power series expansion. This is just I plus Tn plus T squared over 2n squared. Because this thing over here is just e to the n t. Okay. Now, that is what you have for a 3x3 Jordan block in general. In general, if ji is equal to lambda 1, 0, 0, lambda 1, 0 down here, with 1s here, with lambdas here, with 0s everywhere else. And this is possibly a complex matrix in C m by m. We have that this thing is equal to lambda I plus n, where n to the m is equal to 0. And so what this is going to tell us here is that e to the ji t is actually going to be equal to e to the lambda t times the matrix exponential of that thing, which that thing is going to be k is equal to 0 to m minus 1, t to the k over k factorial n to the k, where all I'm doing is that's just writing down the power series expansion of e to the nt, and then just truncating it because I know that all of the terms with m or higher just go to 0. So that is the general form of the matrix exponential of a Jordan block. And so what this is really telling us here is if we want to understand the behavior of x of t, we need to understand the behavior of these matrices. And it turns out that all of these matrices are constructed of products of things like this and this, because these n's, they're just constant matrices. So this implies that e to the at, the entries of this matrix, e to the at, are linear combinations of terms of the form e to the lambda t, t to the k, where lambda is an eigenvalue, k is greater than or equal to 0. And the other thing that we have, which is only important in the case when we have an eigenvalue with 0 real part, is k is only greater than 0 when lambda I, when the algebraic multiplicity of lambda is strictly greater than the geometric multiplicity. So, because the only time we have a non-trivial Jordan block is when the only time we have a Jordan block with a 1 above here is when the geometric multiplicity is higher than the algebraic multiplicity, because that means that we've got more lambdas than we have Jordan blocks, basically. So That's the only time we'd ever have this t to the k showing up with anything other than a 1, right? Because if k is equal to 0, this t to the k just reduces to a 1. Okay. So what we just kind of seen over here is that we can analyze the behavior of this matrix by analyzing the behavior of these particular terms. All right? Because let's think about this. Everything in this matrix is constructed from terms that look like this, that look like eigenvalues. So in your homework, so first off, let's just note here for just 1 minute here. Before we move on here, I just want to make an aside here. T to the k, e to the lambda t. If we look at the magnitude of this thing is of course equal to this thing, if we look at the magnitude for t greater than or equal to 0, I can pull off a t to the k, and then it's e to the real part of lambda, t plus j times the imaginary part of lambda. Sorry, the imaginary and the real, image and imaginary kind of have the same notation. Just use it via context. We're talking about the imaginary part of the eigenvalue over here. What happens here is this part, of course, this is just scalar. Scalar exponentially break up as a product. We need to be multiplying this by a t over here. This thing doesn't contribute to a change in the magnitude at all. E to this thing is always magnitude 1. This is exactly on the unit circle in the complex plane. And so it's t to the k, e to the real part of lambda t. That's the magnitude of this thing. And what we'll see in the homework assignment is that if real part of lambda is less than 0, there exists a constant c greater than 0, such that t to the k, e to the real part lambda of t is less than a constant times e to the 1/2 real part lambda t. And so what that really means here is that this implies that t to the k, e to the real part of lambda t goes to 0 exponentially. That's what we've just seen. So that's that first piece of that theorem that we have. Because if all of the eigenvalues have strictly negative real parts, then all of the entries of e to the at go to 0 exponentially quickly. So if for all lambda, we're going to have all entries of so I don't have enough space on the board here. So if all of the eigenvalues go to have negative real parts, then this is going to imply, let me just erase this over here. By the argument we just had, if lambda for all lambda, then all entries of x of t equals e to the at x of 0 converge to 0 exponentially. And in particular, what we can see, there's just a little argument using what's called the triangle inequality. We're not going to go into this in a lot of detail. This implies that the norm, remember this thing was our measure of the size. Remember, it's the sum of the squares, which we can write as like that, less than or equal to c e to the minus mu t x of 0, or some c greater than 0, mu greater than 0. So that's the one piece. And that's the case that we're going to care about the most, actually. In this class, we are mostly going to be concerned with the scenario in which all of the eigenvalues have strictly negative real parts, and so the size of our system converges to 0 exponentially quickly. And that's just because all of the terms here are constructed with things that go to 0 exponentially quickly. So by just a little bounding argument, this can be shown.
Oh, hey, what's in the exponent there?
What's that?
In the exponent, c to the...
Mu. Mu is just some constant. That's a mu. They're constants that just depend on the matrix here. They're going to depend on the eigenvalues and some properties of the matrix, but they're positive, which means that you've got this positive number, it's e to the minus something times t, so that goes to 0 very quickly. And so now let's deal with sort of the last sort of corner cases here, just so that we understand it. So if real part of lambda is equal to 0 and alg mult equals geometric mult, based on this condition that we derived before, we must have k is equal to 0. So the terms corresponding to lambda are e to the lambda t. They have magnitude of this thing, where the real part is 0, so it's j times the imaginary part of lambda t, which is just 1. So they never go to 0. So they never go to 0. But they don't blow up. Right? So that's what we saw there. When you see in your homework, you have the thing, you're going to get an eigenvalue, you're going to construct a system where the eigenvalues are just plus or minus j, and they're going to be simple eigenvalues. So they have just algebraic and geometric multiplicity 1. So when the algebraic and geometric multiplicity are the same, you're going to have terms in your matrix exponential that just stay at the same value the whole time. It remains bounded. If your matrix exponential remains bounded but doesn't go to 0, that's going to tell you that, you recall that x of t is equal to e to the at x of 0. So if this guy has terms that remain bounded but don't go to 0, then x of t is going to remain bounded but not go to 0. So that is that exact case that we have, where if all the eigenvalues are negative or 0 or with zero real part, and when 0 real part has this multiplicity condition, you can have that oscillation, but it won't blow up. And then any other case, they're going to blow up. So Clearly, this is going to blow up when you have positive real parts just by a converse, just by the analogous argument that we had before. Because remember, when we're doing this thing, the magnitude is e to the real part. So if the real part is positive, it's going to blow up. So but let's deal with the real part of lambda equal to 0 and alg mult greater than geometric mult, which is what we see in standard Newton's equations, which is that thing where it was just kind of going off to the side, and you'll solve for this in your homework. Then we're of course going to have, in this particular case, t to the k, where k is greater than or equal to 1, e to the lambda t. This thing has magnitude 1 by the argument that we just saw. It's equal to t to the k, which goes off to infinity slowly. Right? It goes off to infinity at a polynomial rate. If real part of lambda is greater than 0, t to the k, regardless, for k greater than or equal to 0, regardless of what this is, lambda t is equal to t to the k e to the real part of lambda t, which goes to infinity exponentially. So, or quickly. And so that's it. That's sort of the main collection of results here, where what's going to happen is if you have any positive real part at all, these guys, there's always going to be some term in your matrix that blows up to infinity quickly. And so it's going to mean that there's some initial condition that picks off that piece of the matrix, which allows this state to blow up to infinity. There's always going to be some initial condition that diverges. Similarly over here, if you have anything where you have a real part of 0 with this multiplicity condition, there's always going to be some initial condition that picks up one of these terms and blows up to infinity. So that characterizes stability of linear systems pretty much exactly. All right. Cool. Now the last thing I'm going to talk about, and I'm going to do this fairly quickly, but I think we have enough time because this is a fairly simple concept. Maybe I won't. We'll see. I will get started on it. We'll see how far we get. All right. So let me just recap the theorem. That might be all I'll really do for today. And then I'll just have a smaller homework set than I was originally planning on giving you. So recap. If for all lambda, these are the eigenvalues. So I can do it a little bit more formally. If for all lambda, real part of lambda is less than 0, so we have our system of t is equal to a x of t. There exists c greater than 0, mu greater than 0, such that x of t is less than c e to the minus mu t x of 0. If for all lambda, real part lambda is less than 0, and real part lambda equals 0 implies alg mult equals geometric mult, then there exists c greater than 0 such that x of t is less than some constant times the initial condition in terms of the bound. So this is just a more precise way of writing the stability theorem down that I said in a little bit of a hand-wavy fashion. And otherwise, there exists x naught not equal to 0 such that x of t goes to infinity. So that's the basic setup of this, right? So that's not to say that all initial conditions make you go to infinity in this case, but there's some initial condition that makes you go to infinity. Whereas in this case and in this case, there's no way any initial condition can make you go to 0 because you're just bound, you're just kind of stuck there. Right. Before I move on, rather than me moving on to a new topic, because there's only 4 minutes left in the class, does anybody have questions? I know this was very quick, and I wasn't able to sort of go through and get feedback from people as we go because it's just a different format. But in the time that we have, were there any questions about any of what we just did or other relevant related stuff, or even just the mechanics of how we're going to do this?
I mean, yeah, is this the plan for like future lectures as well? Are you gonna post them ahead of time like you mentioned in that email?
What I really wanted to do was post them ahead of time and have this be more like a question and answer session. So my complete intention was to record these lectures and then do that. And that's what I really do intend to do from this point forward, because I think it's going to be a little bit cleaner that way. We'll see. I'm going to try to do it that way. I can't guarantee that that's going to work, just because my time is extraordinarily constrained right now, given all the situations. But yeah, that's my goal. Yeah. Other questions?
Will the video quality improve at all? Because I'm just finding it really hard to like see what's being written on the board.
Yeah, so no. And I'm really sorry about this. Like, this is a relatively good webcam, all intents and purposes. It's just, I somehow cannot get the lighting to work in here particularly well. I don't really know how to make it better.
Could you put the camera closer to the board so that it fills up more of the screen, maybe?
I could try, but that's going to be a very complex setup because of how the camera is mounted. I could try, but I'm not sure it'll work. I'll try for the next time. We'll see how that goes. I will try.
There might be like camera settings too that you might be able to mess with. I don't know, like maybe it's not like capturing in HD or something. I don't know. I just looked it up quick and I saw there might be some camera settings that.
Yeah, I mean, I'm gonna take a look at this and let me look at this video setting. Oh shoot, man! Enable HD. What the heck? Does that look better? Or not?
It's further away, but you might be able to zoom in or focus more.
Yeah, I don't really know. It doesn't seem to. Let's see how this looks. Did this change anything? No, it didn't. It's not seeming to do anything. Touch up my appearance. Yeah, I don't know. I mean, I saw a thing for enable HD. I'll try to tweak it a little bit, but I don't really know if it's going to get a lot. Yeah, they were kind of stuck with this a little bit.
Are you open to maybe like some suggestions for what other professors have tried in terms of like the camera screen?
Sure.
Awesome. Wait, I can send some over. It's just like I can't read the board at all, which is not your fault, but with like the quality, I don't know if it'll get better like you were talking about.
Yeah, exactly. I don't know if it'll get any better. I'll see if what it looks like on the recording to see if it looks any better. Yeah. Okay. Other things before we go.
You had mentioned extending the deadline for the homework.
I think I'm just gonna make it shorter.
Okay, cool. Thank you.
All right, cool. So if that's that, I'm gonna head out and then see what this thing looks like.
Just one quick question.
Yeah,
Do you have time for like, I don't know, like 5 minutes of a homework question for the homework due today?
sure.
Just like 5.1.
Yeah, I don't know what that is. Tell me what that means.
Yeah, sorry. I don't have it pulled up right now. I can go.
I can pull it up.
Okay, like the analytical one, where it's like you're given ABC and then A minus BKC.
Yeah. We actually literally solved that in class.
Oh, okay. I must have just missed it in my notes.
Yeah. And one of the things, we didn't solve that exactly, but we solved it instead of A minus BKC, we solved it A minus BK, but the method is exactly the same.
Okay. Was that on like the 5th, the last day before we dispersed, or
I have no
somewhere
idea.
back there? Okay, fair enough.
It was during one of those days when we were talking about the PVH test. So the giant hit there is use the PVH test and it really just pops out nearly immediately.
Okay.
Yeah. Yeah, and the other one is PVH test as well, but just a little bit more work. All right, cool. So I'm gonna get rolling. Thank you, everybody. I will do what I can to try to get the quality to look better. I don't really know if I can make it look better. We'll see what we can do. All right. Thanks. Bye-bye.